Hello, welcome back. Today we're going to view a very important topic. It's regarding camera and camera models. Today we're going to talk about pinhole cameras, about the perspective projection. Of course, we want to talk about the camera parameters regarding the Euclidean, geometry, intrinsic parameters, extrinsic parameters, the projection matrix, and the calibration problem in general. So let's start very briefly, talk about cameras. So we can see here like an image, a picture, a photograph actually of a very ancient camera. We can see like there's a sailor on the image, and the camera is showing an inverted image of the sailor. This is happening in all kinds of cameras. This is because the projection that is being used in the cameras. We're going to review it. Well, these kind of cameras are considered like pinhole cameras. What is that? It's a very simplistic model when where you consider actually the camera, the camera lens is like a small uh, pinhole in a dark surface, and the light rays that are being reflected, or in this case, if we have a candle, well, there's some light being emitted, and the light rays go through this small hole and are being projected in the image plane in the surface. But as you can see here, well, the main characteristic of this kind of model is that we get an inverted image at the other side. It's very simple. Okay, we see some rays going here from here below. They are projected in the upper part because they are, yeah, going through this small hole. So at the end we have an inverted image. And sometimes it's more convenient, actually, yeah, talking about cameras, considering the virtual image. We're talking about planes. As we consider as an image plane, this is the real plane, this is the actual plane where the image is being projected. And in our case with digital cameras, would be like the sensor, the CCT plane. But for some convenient reasons, of course, we sometimes talk about the virtual image plane where the image is not being inverted at all. And it is, of course, in front of the pinhole at the same distance than the image plane. So this is what we call the virtual image plane. So let's talk about the perspective projection that is ruling this projection, this pinhole projection. So first of all, the apparent size of the object depends on their distance to the pinhole, to the region, what we call O. For example, in this illustration, the images B prime and C prime, here B prime and C prime, they will have the same height, but A and C, you will see A here and C are really half of the size of B. For example, the distance D from the pinhole O to the plane containing C, in this case is here, is half of the plane containing A and B. So let's talk about it. So if we have a plane where we're projecting the images, this is the pinhole, this is the plane where the images are being projected. We can see that, for example, exactly for two different objects with different object size, like we can talk about, for example, we have B and we have C, okay? And if we see the projection of B because of the distance to the pinhole, we can see that it will appear like having exactly the same distance, the same height than the object C. And they are located at different, actually at the double of the distance. So the double of the distance, yeah, and the double of the size. At the end, it will be projected in the same size. And in the case of A, for example, we can see that A is exactly the same height than C, but as it is like the double of the distance, it will appear like half of the size. So we will discover more about the rules in the next slides. So another thing that is really important is that a common characteristic about the pinhole projection is that the projections of two parallel lines lying in some plane P here, two parallel lines. In this case, we can see there is a plane here. This is a train track, and there are parallel lines. Here we can see at least one, two, three different, even four parallel lines. They will appear to converge on a horizontal line H formed by the intersection of the image plane with the plane parallel to P and passing through the pinhole. Okay, so this is a plane H, this is a plane P where the lines actually are laying, and if we observe this plane that is actually like the virtual image plane, we can see here pretty clearly that the lines are being actually intersecting the horizon at some point. Of course, note that the line L in this case, for example, if we're talking about the line that is behind this plane, has not image at all. Okay, so it's not part of the image. So let's talk about the projection equations of the perspective model. So the perspective projection equations can be derived from the collinearity of the point P. Let's think that this is we have an object here, can be a balloon or something like a ball, and we take a point here, and we can derive the equations from the pinhole model. From the collinearity of the point P, its image P prime and the pinhole O. So we trace a line, okay, a direct vector from P to P prime going through O. Okay, so it's pretty simple. So let's denote that scene point with coordinates x, y, and z, and P prime denote its image with coordinates x prime, y prime, and z prime. Since P prime lies in the image plane, this is the image plane, we have that z prime is equal to the f prime. What is f prime? And we'll start introducing some concept. It's called the focal distance. Okay, that's the distance from the pinhole to the image plane. Since the 3 points P, O, and P prime are collinear, we have the vector P to O, and here is O to P, and it will be equal to O to P prime, but multiplied by some lambda. So it would be just the same vector but bigger or smaller depending on this lambda for some number lambda. So basically the x prime, x prime are the x coordinate in this image plane with this I, j, and k. So the I is the vector in the direction of x, j is the vector in the direction of y, and k is the vector in the direction of z. And then if we observe it, well, there will be also like the same relation with this lambda. So this new x prime will be lambda times the original x here in the same coordinate system, and y prime will be exactly the same, lambda times y. And we can see that f prime, that is the focal distance, or that will be equal also to z prime, will be exactly lambda times the z in the coordinate system for the point P. Well, so from this relation we can solve for lambda, and we have three possibilities. It's equal to x prime divided by x, y prime divided by y, and f prime divided, or z prime divided by z. So if we go further, well, if we solve this, for example, we can solve it for x prime, that is actually the value that we can compute, we want to compute here, the location of x prime in the image plane. We can observe that this is equal to f prime if we solve, for example, if we take these two terms, will be x prime equal to f prime times x divided by z. And the same for y prime. Y prime will be f prime times y divided by z. So that's it. Easy, isn't it? So these equations, if we can see, are valid only when all the distances are being measured in the camera's coordinate frame. That means that for a point, all the coordinates are regarding to the common reference system, that is this one, exactly the camera coordinate system. So the point P must be expressed in also camera coordinates, camera world's coordinate, and of course the P prime will be also in the same coordinate system. And the image coordinates have their origin in the center of the symmetry with the optical axis C prime. See, we see this is the center of the image, and this is the optical axis C prime, and this is center of the image, and then they are projected from one side to the other. So this is simple. For example, let's do a small example. Let's assume that we have a point and the in the object surface, whatever it is, and this is well, these are its coordinates: p minus 10 in x, 10 in y, and minus 40 in z. And f prime is equal, this is the focal distance, to 0.3. Let's calculate the coordinates of p prime respect to O, the same coordinate system. Of course, well, it's pretty simple. We just need to substitute here, and this is 0.3 times minus 10 divided by minus 40 is 0.75. And the same for y prime is exactly the same. 0.3 times 10, positive 10 divided by minus 40 would be minus 0.75. Okay, and this is the point. If we can see here in this coordinate system, the same coordinate system, so I goes in this direction, so if they were taking the piece in the other direction, so it's negative, but once projected, it becomes positive, okay, here in the image plane, because it has been mirrored. And for the y, the same thing. We're assuming that the y is positive here, so it's in this direction, j, so it's positive, but it's been projected as negative, okay? Exactly the same, but because they have the same value, they're projected the same value, but different sign. And finally, well, if we're referring this point p prime respect to the origin O, well, the z coordinate is basically the focal distance, 0.3. So it's pretty simple, isn't it? Okay, so let's go further. So, but we were talking about this case, but in general, we will elaborate more things. So this is basically the origin. This is what we call normalized image plane, and this is what we call physical retina. That is like where the CCD sensor inside the camera lies. However, we will start talking about this normalized image plane. Well, if we recall these equations to get the point x prime and y prime, and if we assume that the f prime, I mean the focal distance, is exactly equal to 1, then these are the equations. The equations are being simplified. So u prime, hat, we can say, with small hat, will be equal to 1 times x divided by z, and v hat will be equal to y divided by z. So it's been simplified, and the point P, that is the corresponding point to P, this is a pinhole, and the normalized image plane will be equal to 1 divided by z times an identity matrix. We can simplify, we can more than simplify, and we can represent it differently. We can represent it through matrix algebra. So it will be represented by an identity matrix and multiplied by the point P, that is also a vector, and it will be an extended vector, a homogeneous vector. Okay, this is a representation. It's pretty simple. So it's exactly the same operations, but in this case, this is the identity matrix, this is the zero matrix, and this is the vector P, the original point, and we're extending it. Well, actually extending it is not really necessary. We could also represent it like this, just the identity matrix. You'll be multiplying the x, y, and z, p a point, and we're going to call this like the normalized point P in the normalized image plane. So basically, there will be their coordinates u hat, v hat, and 1. So it's pretty simple, pretty straightforward. Well, let's go further. and let's talk about the physical retina. In this case, that is what will be actually happening the whole time. We're not just talking about this normalized plane, well, the general case. So in the general case, we have U and V, and U and V are not expressed in meters. See, they are expressed always in pixels because we need to find out where is the point in the image plane that correspond to the physical point in the coordinate system, in the camera coordinate system. So first of all, we have U and V. Those are the location for the pixel corresponding to P. So it's exactly the same. F, this is the focal distance that is being expressed in meters. Then we have X and Y, X, Y, and Z, they're expressed in meters. And we have a new variable, this is K and L, two variables. And K and L, actually there's a relationship between the distance and the number of pixels in the CCD, on the sensor. This is how many pixels per meter. So in this way, we are able to convert from meters, if we multiply this F, that is the focal distance in meter, times this K or L, that are pixel divided by meters per meter, the result is pixels. So in this way, we can compute how many pixels will correspond to exactly this ratio multiplied by this variable. So you will be in pixels. So then let's go further. This is, if we take this representation and then we put it here inside our all matrix, we will see that we can represent exactly the same operation, but this time it's not just one, but the term is K times F and L times F. Okay? Well, let's go further. If we remember, we were talking about the center of the image, but it's not happening like that in the final image. The origin is not in the middle of the image, it's in this part here below. We can define the origin. So we need to display the origin of the image as well, of representation. And for that purpose, of course, first what we do is we simplify it. We assume we give like a letter, an alpha Greek letter, to the product K times F, and we assign the name beta to L times F in order to simplify. And we add a displacement U0 and V0 that correspond to the amount, actually an extra displacement, to locate the points, the origin, not here in the middle, but here below. For example, if we have here a value that could be negative, we know that this point, for example, here, well, we don't have negative numbers in the image pixel locations. But what we do is pretty simple, pretty straightforward. We need to sum half, of the width of the image and plus in the x, what's in the horizontal x, and we need to add also like half of the size of the vertical size in the y coordinate. So just by adding this, that is u0 and v0, we can displace the origin, and each point that lies in the negative area will become automatically like just positive numbers. So it's pretty simple, but let's go further. So we're almost done, but there's an extra thing. Let me go back. So if we review here the matrix, we will see that we have an alpha, we have beta, we have u0, v0, and our vector in camera coordinates. Perfect. But what else? Well, sometimes happens that if we don't have what we call square pixel, that is, we could have like a bit of skew, and this skew will produce that the axes are not absolutely perpendicular. So in this case, we have to add an extra term. This is the cotangent of theta. Now theta is the angle between the u and v actually axis, and then the same for the rest of the thing. In the case of v, we need to divide beta times sin of theta. And well, this will be the more complete matrix operation that will implement this perspective projection. So finally, well, it's very common that the cameras, they don't have a skew at all. And if pixels are considered squared and s the skew factor that we're calling skew here and here, this is the term that corresponds to the skew, is equal to 0, then the focal distances alpha and beta will be equal, exactly equal, because yeah, f will be exactly the same, and the main point u0 v0 is equal to the image center. I mean here u0 and v0, as I told you before, will be exactly the image center, so will be basically the width divided by 2 and half of the height also. So it's pretty simple. It looks to. Okay, and finally we call the calibration matrix to this matrix K that is basically described here. The alpha, beta, and well, and we have the u0 and v0, so it's pretty simple. So let's talk about these camera parameters in the Euclidean geometry. So in practice, the world and camera coordinated systems are related through physical parameters as focal distance length, pixel size, the location of the center of the image, and the camera orientation. That is, if you remember, this is valid only when both the point and also the projected point are described using a common reference system. This is a camera reference system. But we have what we call intrinsic parameters. They relate the camera coordinated system with an idealized pinhole camera image coordinate system. Are precisely what we did. We're relating the real with an idealized pinhole camera model. But there's another kind of parameters, are called extrinsic parameters, and they relate the camera coordinated system with a fixed world coordinate system and specify its location and orientation in space. So what happened that most of the time this is not the case, because of course sometimes there's a world coordinate system. But let's go back and let's talk about each one of them. So this is familiar already for us. We have talked about this matrix, but without giving it a specific name. But now, well, let's give it a name, and the name are intrinsic parameters. So basically, the intrinsic parameters, they project a 3D point x, y, and z in the camera coordinate frame x, z we call, into the image plane. How? We can implement that by doing a multiplication xz times k. This is the calibration matrix, but the result, as you see here, is missing one term. If we just do the multiplication, it's missing this term, 1 divided by z. Well, this is not a problem, but this is just a simplification. But what we will have is that we have u, v, and w precisely, this new value, this value that won't be 1, after doing the multiplication, is called the scaling factor. And this scaling factor will correspond exactly to the z coordinate. So if we multiply these two matrices, well, this vector by this matrix, we will have like a vector that will be precisely, will have still like a scaling factor. So, where alpha and beta are the focal lengths in pixel units, is basically, if we remember, this k times f, basically is the focal length, but in pixel units, not in meters. It's the same for beta. This is for the horizontal axis, for the vertical axis, and we know already what u0 and v0 are the image center in pixel units as well. And s is what we call the skew parameter. So what do we do in order to get like the corresponding pixel p prime in a physical retina? Sorry. So in order to get this point in the physical retina, it is necessary to normalize x, because what we will get after doing this simple matrix multiplication will be like a vector, but in order it won't be like the final pixel coordinate vector. In order to get this final value, we need to divide it times 1 divided by w. Precisely, we take this value directly from here. So if we do this, then we will get the right number and the image. Okay? So, but let's talk about the general case. we were talking about the points that are referenced, that are described using the camera coordinate system. But in fact, well, it happens that there is always, well, normally there's always like a global or world reference frame here. For the general case, when the point P is given in world coordinate, this is an external, a prefix coordinate system that is centered in some point in the world, and it has I, J, and K coordinates, actually axes, is given in world coordinates X, Y, and Z, capital, and we will use an extended vector, a homogeneous vector. Then is necessary, first of all, before computing this point P prime, it's necessary to transform it into camera coordinates. How do we do that? Well, it's pretty simple. We remember about the affine transformation. Well, all that we need to do in order to transform one reference frame into another reference frame is actually implement a translation from one to the other and a rotation. So that's implemented through a rotation and translation matrix as a combination. So, as I said before, an affine transformation consisting in a rotation plus a translation between the world coordinate system and the camera coordinate system must be performed in order to put the point P in the camera reference frame, not in the world reference frame, but in the camera reference frame. And, well, we can build like a matrix composed directly from the rotation matrix and translation matrix. We will describe it later. But X, now this capital X is referring to the point in world coordinate system. So we will do an operation, first of all, for transforming X times the rotation and translation, a single matrix, into camera coordinate frame. And once that we have this camera coordinate frame representation from the point P, then we multiply by the calibration matrix K. So how do we do that? Okay, let's review more in detail the values of the matrix R and T. So, as we said before, a projection matrix can be decomposed into two components, intrinsic and extrinsic parameters, as is described by this formula. So this is our calibration matrix for intrinsic parameters, K, and we called extrinsic parameter matrix actually to this new matrix that is composed from a rotation and translation matrix. And it's basically, this is a R is a rotation matrix, and T is a translation matrix. So the intrinsic is 3 times 3 is 3 rows, 3 columns, calibration matrix K, and for the extrinsic matrix we have 3 times 3 rotation matrix, well, and 3 times 1 translation vector, but they are represented in a single matrix for simplicity. And we still have here, we remember if we do this multiplication, at the end we will end up with a vector u, v, and w that has the scaling factor. And again, if we remember, we need to divide, we need to rescale, normalize this vector in order to get the final location of the point P in the image, I would say in the image plane for the final image pixel location. Okay, so, but let me go back a bit. If you see, well, this matrix will be permanent, will be consistent the whole time. It will never change for a camera unless you change the focal length, for example, or you change the resolution, will be difficult, or you make the image bigger. Probably you can take bigger image or smaller image with the same camera. But in general, if we don't change at all the parameters, it will prevail the whole time, so it will be always the same. And if we keep with the same, this is useful because we can actually leave the world coordinate frame also. It must be fixed. But if we're doing some kind of experiment, or we're doing some kind of work with robots, and we define already the world coordinate system's origin, and it remains the same, then we can do something. We can simplify. We can multiply these two matrices that won't change at all, and we will get like a 3 times 4 final matrix that will be just a single matrix, and all that we need to do will be multiplying by the point P in our coordinates and getting the vector. So that's it. So we can name this matrix like M, and this matrix can be written explicitly as a function of 5 intrinsic and 6 extrinsic parameters. And the intrinsic will be alpha, beta, u0, v0, and theta. And the 6 extrinsic will be the 3 angles that define the rotation and 3 coordinates that define the translation. So we can simplify. We can say that matrix M will be the multiplication of the matrix RT and multiply by the matrix K, the calibration matrix. And these are the values. Okay. And in this case, it will refer to R1 transpose. We're talking about the 3 rows of the matrix R, and Tx, Ty, and Tz are the coordinates of the vector T. So we can see basically we can represent it simple. And M, this matrix M, is defined only on certain scale. The scale that you of course depends on the point P, but can be simplified. Let's make another exercise. So in this case, given the following calibration matrix K of an iPad Pro camera, I actually have got these numbers by using the APID-CD calibration tool. Well, we have the numbers, and we know that the image resolution was 1280 times 720 pixels, and it has a focal length of 3.3 millimeters. The goal is to compute the pixel per meter values K and L. I mean, the way of transforming the focal length into pixel size, I would say pixel length, and the pixel aspect ratio K divided by L. So it's pretty straightforward. What we take is we just take this thing that was the already as K times L, and we solve it for, in this case, K. So all we need to do is to divide it by the focal length, that is 3.3 millimeters, and we can see it's about 300,000 pixels per meter. Okay, in the case of the this was the horizontal axis. In case of Y, or vertical axis. Well, this is what OpenCV is giving us, and then we do the same exactly because it's the same focal length for X and Y, and well, it's about the same length. It's 300, almost 300,000. And if we divide K divided by L, well, we can see this is almost 1. Okay, so we assume that we have what we call squared pixels. So the size of a pixel in X and Y is the same. Great, so let's do a more complex exercise. So let's think that this time, for example, this time we have like the point P in the world coordinate system, and these are like this is the location, 10 centimeters in X, 20 centimeters in Y, and minus 20 centimeters in Z. So it's clear this is the camera origin, but this is the world coordinate frame. So we have something that is in this direction is Y, it's I, so it's 10, and then J for Y is 20 centimeters. 20 centimeters, okay, and the point is behind in this direction. K is going in this direction, 20 the other direction, so it's minus 20 centimeters, okay. And then this is our camera model. We have the focal length is 35 millimeters. It is actually, well, there are some, not speculation, but there is some theory that this is precisely the focal length of our eyes, 35 millimeters. That's why there are some old cameras, well, all the 35 millimeters cameras are based on having, these lenses, this objective focal distance similar to the human eye. So that's why this format, this focal length is pretty, or was pretty popular for professional photographical cameras. And then in this case, let's calculate. The goal is calculate the coordinates of P prime in the physical retina. I mean, the final image coordinates in the final image coordinates for the given pinhole camera with these parameters. So let's see, for example, IW. So in this case, yeah, we see the x-axis. Yes, the x-axis in the world coordinate. It's pointing. Well, it's more or less. I mean, it's perfectly drawn, but should be a little bit more like that. But they're the same, pointing in the same direction. We are assuming that they're pointing exactly the same direction. JW here for the y-axis are exactly the same direction that J for the camera coordinate system, and finally KW, I mean, is for the Z axis is pointing in the opposite direction. So the world coordinate frame goes in this direction and the camera goes in this direction. Okay, so KW is equal to minus K. And we will do that. We assume that the image size, yeah, the image size is 1920 pixels times 1080 pixels. And we assume, as we said, a focal length of 35 millimeters. And we assume that the pixel aspect ratio is equal to 1. So we have square pixels. We have no skews. And no, sorry, no, we have no skews at all, to say it wrong. So we have no skew. And finally, K and L, I mean, you remember these parameters are actually, yeah, 300, yeah, actually is 300,000 pixels per meter, or yeah, times 10 to the fifth, so pixels per meter, so 300,000. And we assume that our world coordinate origin is in the 0, 0, 0 location. Yeah, that's the common thing. And our camera, the camera origin posed in the world coordinate system, respect to this point, will be 30 centimeters. So in this direction, 30 centimeters. Then 10 centimeters in y, so 10 centimeters, a little bit up. And as this is the origin and it's going this direction, will be negative. In this case, will be minus 90 centimeters. Okay, so let's get to work. First of all, what do we need to do? Okay, we will put the matrix K. So as we know already, we need to multiply K, that is 3 times 10 to the fifth, yeah, here, times the focal length. But what's the focal length? 35 millimeters. So but remember, it needs to be in meters. So we need to, okay, we need to do something here. It's not for the 35, but will be 0.000, no, sorry, 0.035. So this is 3.5 times 10 to the minus 3. The same will be exactly for the other axis. Will be exactly the same. And then we know the size of the image, and we will divide it by 2 in order to get the origin. That's it. So those are the values: 1050, 960, and 540. So we have K. Great. What else? Well, we need to build the RT matrix. And, well, as we said that I will be equal, well, this will be 1. J will be equal for both, is also 1. But finally the K, yeah, actually, this is a rotation. But actually, well, in this case, we just put here minus 1. We have a rotation. Actually, it will be 180 degrees rotation in the K or in the Z axis. So will be equivalent to just putting here minus 1 because 1 will be inverted. And of course, here, if you remember, we have the camera pose. In this case, the camera pose, this translation that must be done for each one of the points in the world coordinate system to the camera's coordinate system should be the negative in this case of this value, because this actually are the camera pose in the world coordinate system. So we need to do the opposite translation. So in this case, in order to put something that is in the world coordinate frame, in this case is the camera pose, or the point in the camera coordinate frame, we need to put it minus 0.3 in meters, minus 0.1 in 1 decimeter, and 0.9 because we're referring a point in the world coordinate system into the camera coordinate system, and here the data that we have is the opposite. The world coordinate system is 0, 0, 0, and the camera was referred to this, so we need to do it the inverse translation. Okay, so let's continue. So now we have our in order to compute our x vector, we need to multiply all these things. So first of all, we have the K, the calibration matrix, then we have this RT matrix, and our point P also in meters. So this is the point, 10 centimeters, 20, and minus 20, 0.1, 0.2, and minus 2. Okay, let's do the multiplications. First of all, we need to multiply. We will do this thing. We will multiply, K times this RT matrix, and we'll get, well, the matrix M. And we do that is, we can see this is actually we're multiplying. It's pretty straightforward. This is exactly the same here. And here, as we have minus 1, well, this column would be negative. And at the end, we will multiply 1050 times minus 3, plus this is 0, plus 960 times 0.9. And the same for the third column. For the row, this will be 0 times minus 0.3 times plus 1050 times minus 1 plus 540 times 0.9. And in the third row, we will have here 0 times, it is 0, this is 0, this is 1 times 0.9. So it's pretty easy. So we do the multiplication. This will be the matrix M. Yeah? So this is a matrix that won't, well, if we don't move the camera, of course, and we don't move the origin, well, this is our matrix for doing the transformation. Well, so let's transform it. Let's multiply our point P in the world coordinate frame, that's 0.1, 0.2, and minus 0.2, sorry, and 1. If we multiply, well, this is what we get. Here we see this is 846, 699, and 1.1. Okay? So finally, in order to get the coordinates of the point in the image corresponding to the point P in the world coordinate frame, we need to normalize it. We need to divide it by this W, and if we divide it, we get this 769.09 and 635.45 and 1. So we can assume that our point P in the image will correspond to 769 and 635. Okay, is that right? Well, we can check it here. Let's go forward. Let's go backwards, sorry. So we have a point P that is in this side. This is, I would say, go in this left direction, and it needs to be mirrored. In this case, this arrow is not precisely correct. It should go the other direction. So the corresponding point, if it's here top, will be down here. Okay, this will be 0, 0. Remember, this will be the origin in the image. This will be 0. Will be positive, and this will be positive. It will be seen like if this is the camera and this is the CCD. If it's a small screen, this is behind your camera. Well, this is what you're looking from this direction. Okay, so if we see, well, the points will be here, and let's check it again. Those are the values. Okay, 769, 635 that are below, below the center of the images. So, well, so that was a good exercise. Well, just a numerical exercise. We didn't need to do that, but well, probably in your exam there will be sort of kind of this problem, but not so complex. But probably something very simple, just to play a bit with the projection, perspective projection equations. But under this concept, let's talk about OpenCV. Let's talk about things that calculate this thing more easily than just doing by hand. Well, under this context, the calibration problem can be modeled as an optimization problem, where the discrepancies between the observed characteristics on the image and their respective theoretical location in the world frame are being minimized with respect to the internal and external camera parameters. There are many techniques. Well, we can use least squares techniques, Linear calibration, use point-based, line-based, radial distortion considerations, nonlinear calibration, analytic photogrammetry, many techniques to compute these intrinsic and extrinsic parameters. But let's use something that is pretty common. We're talking about something that in the real world we're using lenses. We're not using just pinholes. We're not just using cameras with a small hole, but using big lenses. And these lenses add some curvature to the camera image, to the final image. And we use normally, what we use is something like a pattern, an old pattern, in this case a chessboard pattern, and these lines will appear more curves in the final image. If you see here, if this is like a straight line, due to the internal optics of the camera lenses, they are not, of course, they're not flat, and they're distort image. We will have this curvature. This phenomenon is known as radial distortion, and the camera calibration must also calculate the distortion parameters in order to correct them. We won't review deeply this topic of distortion, but it's just by now it's just important to know that there's a distortion in the image, a curvature induced by the use of lenses. So what do we do in OpenCV, or what do we do in general to calibrate? Well, what we need to do, of course, is first of all we need a pattern. We print the pattern, we put it on the flat surface, and then we start taking several pictures, at least 10. We need to take several pictures moving the pattern within the camera field of view, but in different locations, orientation, but must be seen completely. So we take several pictures. After that, well, we can use some functions that are included in OpenCV, like CV, to find chessboard corners. So it will be very, not very simple, but very doable. It's quite easy. We have such pattern just to look for the high intensity and low intensity areas in order to find like these corners. This is done with the find chessboard corners function in OpenCV. So this is one output, for example, a plot of what this function does. And then later we use an OpenCV function, this calibrate camera. Well, this function is helping us to compute intrinsic and extrinsic parameters. Of course, the camera matrix, the distortion coefficients also, and rotation and translation vectors. And finally, this is the original image. We can use OpenCV function, this onDistort, that we give the parameters, all the parameters that were calculated with the calibrate camera procedure function, and we use them to ondistort the image, and we can see here like the undistorted image. So this is pretty straightforward. So your first exercise, well, regarding this topic, will be implementing the camera calibration method. Basically, as always, as usual, is basically copy and paste some code described here. Let's check it. Let me jump. And here, this is the page. So it will refer to this page. You will see this is the OpenCV camera calibration example, and you will see precisely some of the image. You will see here the camera matrix. This is the calibration matrix, some values, and you have here some pieces of code. So you just need to take this code and put it to run. First, this is the section that will compute, that will find the corners in the chessboard. Then this is a command, calibrate camera, to get the parameters. Then you need to run this ondistortion. Here is the ondistortion. This is some intermediate step to get a better approximation. You use ondistort, and well, finally, you can understand the image, and then here it is, and you can crop the new image. Here is not. If you can see, for example, you can see a black area because if the original one was curved, well, what it's doing is like if you were pulling from both sides. If you're pulling, if this would be some kind of plastic bag, if you pull at this point, well, you will see that it's been pulled from here and there, and you will see like a small black area. Okay, this is well, not so noticeable, but it is there. And then, well, this is just a part. It's not important that you implement it, but it's important at some point if you want to do that. is a part for, knowing how good your approximation was. So I would show you what this thing should do. And by the way, about the set of images, I prepare already like a big set of images for you. Those are just two examples. They are located in the G drive in the Robot Visual Pictures Calibration Easy external camera folder. Well, here's the drive, and if you go here, you will see calibration. And we have several. We have 3 times. We have calibration patterns. If you want to do it yourself, okay, you can try it. Perfect. But I did it for you. I did already take the pictures. And we have easy external camera. Yeah, those are several pictures. Let me just open one. That's it. Okay. You have lots, like 40, 43, something like that. Okay. So you need to take this code, and instead of loading just one single, no, it's not one single image. Here is been described. Here, look, yeah. Remember to adding the path, the right path, to load them, and well, you will get something like this. Camera calibration, you will see. So basically, the program will open the images, and then it will find like the chessboard corners, and then it will, in this case, what I did something extra that is not in the program. Look, this is what is being done. First of all, it's opening the images and start looking the corners and computing the parameters, and takes several until it gets to some minimal. Here, for example, it just 2 images, probably one more. If not, in my case, it will continue with the calibration and it will do the undistortion, the correction. We'll see. Take some time. And if you can see, well, these images are not so distorted. Okay, they're okay. Those are the corrected images. So it's, well, not really not slow, but it is there. Okay. So what I'm doing is actually just displaying all the images but undistorted. Okay, so this is not a big trouble. And it's pretty useful, especially if you want to measure something out of the images, for example, some dimensions or simply distance between points in the image. Okay, great. So this is the first part of the exercise. So let's go forward. But this is a case if you take a look to the Google Drive, you will see there's something at this top. And if you remember, this autonomous car, well, this small car, actually, the one that we're using, has 2 cameras. So what? Well, what I did is that I took also some pictures with the fisheye camera, and okay, this is more interesting because we will do also the calibration of that camera is in top. Now let's open one of them. Oh wow, this is really a distortion. Okay, this is really distorted, but okay, fortunately, in OpenCV there's also procedures, special function for calibrating such cameras. I mean, actually it's the same, but it's just that the optics introduce a lot of distortion. It's really severe, and but fortunately, OpenCV 3, not in version 2, but in version 3, incorporates also a fisheye calibrate method and fisheye undistort image method. Oh, great! So let's take the second exercise. You need to implement the fisheye camera calibration method. Basically, again, copy and paste the code. This is described here. Let's go there. And you will see. Okay. Okay, there it is. So there are always problems, but in this tutorial, if you go down, okay, we have already a lot of images. By the way, I also added a lot of images, so this is the code. Basically, it's again copy pasting, but this is divided in 2 sections. The first section computes the camera calibration matrix. You have 2 parts. It's called Python, well, it's calibrate.py. You need to run it. If you run this small program, you will get something like this. K is the calibration matrix, and then D is some it's a vector with some parameters for correcting the radial distortion. We won't talk about them, but we just describe that there are some values that need to be used to actually undistort the image. Okay, so you will get this value. And for undistorting, you will have a second program, undistort.py, where you will define the set of images. Somewhere here, for example, well, here we are talking just reading image path, but you will define here, not the image, you will add the image path and the names of the, not the names, I mean the directory where you will be reading the whole image set, and you just need to call this undistort function. Where is it? Here in my shape. It is initializing the undistortion engine. Here it is, and this is the code. CB2 remap, here init undistort rectify, undistorted image. So basically, so you will see what is the result. Okay, the result. Oh, sorry, it's here. But this is the first part. So you will implement the calibrate and the undistort. And well, after doing that, let me show you one of the results. If I go here, let me log into the drive. Here it is. Those are the pictures. I will run it. I think I've already run it. This is top. Somewhere should be the undistorted. Okay, these are the original ones. Yeah, the original ones. Now I will run my Python script. Let me check what's the name of the script. Okay, is calibra is undistort. Fish eye undistort. This is. Let me run it. Let me just Python and fish eye undistort.py. Okay, take some time. Opening the images and okay, look. Pretty nice, pretty nice. Look, this is the original image and this is the undistorted one. Okay. And what is it useful for? We will see that later, because we're building actually something for robotic use that we were using. Do you remember about our optical flow and things? Well, we needed to correct this, this camera, this pointing towards the ceiling. Okay, so great. And then finally, okay, the third part will be, well, quite straightforward. You need to modify your robot vision script video pre-prompt. Do you remember the last time you added here like the Shai-Tomasi preprocessing actually to display the undistorted, the corner detector for the fish eye camera video. So what you need to do again is to add here into your here video prepper undistort. Let me check what is the good one. Undistort, so you need to have, look, is what I did, it's exactly what we have, or I describe in here exactly like the parameters, but there's a small but, and I will talk about it. What I'm doing here is, yes, this is undistorting and rectifying. If you see. So basically, after opening the image, I'm understarting it, and then I'm doing some things here. Okay, I'm doing more things. But there's one tiny thing. It's not so tiny, but you need to find out yourself what. This is the thing. Well, if you remember, the original videos that I posted in the G drive, Yeah, they are much bigger than the ones that we are using for actually running the examples. For example, this is the case of the top camera. Okay, we're talking about a resized, reduced video. So the original video size, yeah, let me go back. The original video size here in the Google Drive is the same. Let me just go to Robot Vision. Let's check the videos. If you remember, there are several versions. These, the AVI, are the original ones, but these 480 versions, well, both in their move, yeah, and their AVIs, but with 480 suffix, they mean that these were reduced. So in the case of the of some videos, for example, in the case of the omnidirectional of the fisheye camera, the original video size is 1920 times 1080 pixels, the big video, and the reduced version, the small one, the one that we will use for displaying or correcting, understating the image. Oh, sorry, I will display it. It's videos. This is, yes, this is the one I'm talking about. Let's open it. It's much smaller. Look, this is the version that we're using. And the original one is really big. Then, yeah, the reduced version is 640 times 360. Then, and this is the point. If you remember all our images or calibration images here are the pictures, exactly what we have in the G drive tab. Those are the original one. Look, 1920 times 1080. So here the challenge would be that once that you get the calibration metrics for this set of images, you need to apply, you need to do something in this calibration matrix K. That's not too complex at all, but you need to do something in the parameters in order to apply them on the video that is being resized. Okay, so it's not really a big deal, but you need to do something in the K matrix. Okay, otherwise you will get something pretty weird. Okay, so this factor, this rescaling factor, must be also incorporated into the intrinsic calibration matrix K that you already calculated with the OpenCV calibration functions somehow in order to understand the resized version of the camera fisheye video. So it's not too complex, but it's a good exercise if you understood correctly the lesson. So finally, what should you deliver? Well, as usual, you need to send your code per email. Well, you need to just name your files, calibrate, and distort, and finally this video pre-pro. Okay? It's important, remember, to have the right path. Yeah, well, I think that if you do like this, just with the single quote, and this slash dot dot slash, this is the relative path. So for those people that are working in Windows and had some troubles defining like the long path, you can do this thing. But don't worry, if you have just a full path, I can, yeah, of course I can just substitute it, but I think the right way to do it is actually putting like in this notation. Okay, so that's it for today. Will be really important. Well, just to make a brief summary of what we saw today. Today we talk about these camera models. We talk about the inversion thing that happens on the image in the pinhole camera. We derive like projection equations that are quite simple between the points in the camera frame and the points in the image plane. We made some examples. We talk about normalized image plane. We talk about the physical retina and the final way of calculating the points. Some parameters. We talk about intrinsic and extrinsic parameters. Remember that we talked that the operations, produce some vectors that has an scaling factor, and this scaling factor needs to be removed or normalized in order to get the final position of a pixel of a point in the image. We talk about general case and matrix algebra notation for computing this more efficiently, using a matrix from intrinsic and extrinsic parameters. One extrinsic parameter relates like a point, the board coordinate frame, into the camera coordinate frame, while the intrinsic parameters refer the point into the image plane in a point in meters. They're remapped into that point in pixels. Okay, so we did some examples, and okay, we did a couple of examples about how to convert, and we talk about a way of calibrating the cameras in OpenCV and some homework. So basically that's all for today, and well, please have fun, and we'll see each other the next time. Thank you very much.